Hi, I'm Geoff Clarkson, and I'm the founder and chief technical officer of UTComp. UTComp is an engineering and inspection company for FRP composite assets. I'm also the creator of the Ultra Analytics non-destructive testing system, which is in use worldwide in a wide range of industrial sectors. We are an engineering and inspection company specializing in fiber reinforced polymer and other composite materials. We're revolutionizing the way that industry, the mining industry and others inspect their FRP tanks, pipes, and other assets to give them superior reliability, safety, and return on investment. Composites actually differ quite a bit from steel in the way that they perform, and for that I'm going to illustrate with two charts. For steel, which is a common material that a lot of us are familiar with, the strength of the steel remains very constant, in fact basically constant for its entire life and service. But when corrosion occurs, the thickness will drop off, as shown by this green line. The thickness drops off because metal is corroded away from the original material. For FRP and polymers, we have a little different situation. Usually the thickness, still shown as a green line, stays constant. The tensile strength, which is the strength that we usually talk about with steel in the blue line, the tensile strength and the tensile modulus of the FRP and the polymer often stays somewhat constant. It drops a little bit depending on how much polymer is in the mix. If it's reinforced, it doesn't drop off very much, and that's what I'm showing here. But what does happen is that the polymer is significantly damaged well ahead of the reinforcement. And in fact, I'm showing here the changes in the stiffness or the elastic modulus of the polymer or the resin after exposure or during exposure to chemicals and stress. And you can see how profound this drop is and how different it is in behavior from steel. An example. This is for an FRP storage tank that we've actually been involved with for 26 years now. But in the first 18 years, a few things happened that were fun. First of all, when it was brand new, the stiffness and the thickness were exactly as designed. They were 100% of the design strength. Good news. After 14 years, we removed a piece from the shell so that we could put a new nozzle in. And we found that the stiffness of the material in the shell had declined to 60% of what it was when it was new. Again, the thickness hadn't changed. As you can see, 18 years later, or 4 years after that, 18 years after startup, when we removed another section to install another nozzle, we took the same measurements and we found that the decline had gone to about 53%, and still the thickness was unchanged. This curve here, this dotted line, shows basically the same curve that we just showed. These changes are dominated from the polymer. They're created by changes to the polymer. And in fact, we can measure it as a change in the flexural stiffness, in other words, the change of the resistance to bending in a 3-point test. We've just talked about how stiffness has declined and reduces in time or after exposure to stress and chemicals. Well, at the same time as the stiffness is reducing, and that's actually the stiffness of the polymer that's really telling us that. That's its resistance to stress. As that is reducing, so also is the amount that the polymer can stretch before failure. So if it could stretch, say, 5% of its length before failure when it was new up here at 100%, then down here when it's at 20%, and this is for heavily damaged polymer, when it's down at 20%, it would only be able to stretch 20% of 5% or 1% before it fails. So we actually have got a changing situation because we know that the amount of strain or stretch that the material can experience declines as it's damaged. And so what happens now to the tensile strength of the material, because that's something that we took a look at. Well, I'm showing here a chart that shows how much tensile strength is retained after the polymer is significantly damaged. And I'm showing it against the amount of reinforcement. As we increase the amount of reinforcement, you can see that the amount of tensile strength retained, the amount that remains, increases, and it gets up to the point up in this zone here where you can be pretty sure that that you've got 80% to 95% of the original tensile strength in the material. Now, of interest, this corner point occurs just about the point where we start to use the amount of reinforcement that's used for most structural purposes like tank shells or piping and so on. Below this point is reserved or dedicated for corrosion barrier or corrosion protection structures that don't usually are not expected to contribute to the structural strength of the material. If you have any questions about this, please give us a call, me or Joanne Watton. Our contact information, of course, is on this slide, and we would look forward to hearing from you and talking about any of your questions in terms of the damage mechanisms that take place to FRP and composite materials. Thank you.